approach with Sentinel-2 satellite images, and it was done in the context of my master thesis. So the plan is the following. We will begin with the introduction, presentation of the study area, methodology, and final results and some conclusions. I just want to underline that the project was conducted in the context of the EOTime, which is Earth Observation Technologies for Irrigation in Mediterranean Environments. And as an introduction, so as you know, in the 21st century, agriculture continues to be a fundamental instrument for sustainable development, poverty reduction, and food security. However, irrigated agriculture uses more than 70% of the fresh water worldwide, which means that we have to use it efficiently and for food production. But unfortunately, this is not the case because we have some leakage in the poor performance of the system. So this is why performance analysis is required to improve management activities and to identify appropriate modernization or rehabilitation measures. And to do so, we have to estimate the irrigation water requirements in order to compare it with the actual water supplies. So recently, many studies have been carried out using remote sensing, and the results showed an increase of irrigation efficiency, which was achieved because of reduction of water volumes, and the forecasts are delivered to farmers with a simple and intuitive interface, whether it is a web or mobile applications. So in this study, the performance analysis of the on-demand irrigation system was assessed using the estimated irrigation water requirements through the estimation of crop evapotranspiration based on satellite images. Now let's move to the presentation of the study area. So the study area was, the Sector 6 of District 10 in the Sinistra Olfatto irrigation scheme, which is located in southern Italy in the northeastern part of the Apulia region, the province of Foggia. So the distribution of the cropping pattern in our study area is mainly based on vineyard, which represents 50%, almost 50%, early peach with 24%, autumn-winter cereals 80%, and a little bit of apricots, olive, and vegetables. So this is the layout of our irrigation network. So here for the methodology, first of all, we collected Sentinel-2 images, and from these satellite images, we were able to derive the albedo, the leaf area index, through the calculation of weight difference vegetation index. And directly from the leaf area index, we were able to derive the fractional vegetation cover, and the crop height was fixed to 1.2 meter. And using meteorological data that was derived from the ERA 5 atmospheric model, we were able to estimate the crop evapotranspiration and also the effective rainfall. And from the two components, we were able to estimate the irrigation water requirements. Now, since we have the registered volumes at the Sector 6, we were able to compare the volumes, whether the estimated and the registered volumes, and combined with the farmer's behavior, we compute the upstream discharge of the Sector 6, and finally assess the performance of our irrigation system using COPAN. So for the satellite images, first of all, our study period was from June 1st to September 13, 2019. And during this period, we find 40 days where we have available Sentinel-2 data. And the data was downloaded from the Copernicus Open Access Hub, Level2A, which means that they are atmospherically corrected. So for each Sentinel-2 image, we have 10 spectral bands in the cloud mask. And the bands are the ones who are highlighted in red. So in the total, we were able to process and use 40 Sentinel-2 images. So the meteorological data, they were derived from the atmospheric model, this fifth generation of European Center for Medium-Range Weather Forecasting Analysis, as a substitute of ground-based meteorological data. Now for our remote sensing derived parameters, first of all, we have the leaf area index that was estimated using the simplified Clever's leaf area index by reflectance model. So the calculation of the leaf area index were based on the weighted difference vegetation index, and for the weighted difference vegetation index is estimated through the near-infrared infrared reflectance and the soil line slope, which means which is the ratio between the near-infrared for the bare soil reflectance and the red for the soil reflectance. Okay, with the difference vegetation index at infinite, which means the maximum, where we have the maximum of canopy cover, and it was derived from the Western histogram. And finally, the alpha parameter that was which was calibrated using the leaf area index derived from SNAP that uses the that was implemented in SNAP actually. The second one is the fractional vegetation cover, which is directly derived from the leaf area index. The albedo, which is the weighted sum of surface spectral derived from the atmospheric correction. The crop height was fixed to 1.2 meter because we made an assumption that the influence of crop height on the value of crop evapotranspiration is small for different values of leaf area index, and that was proven, has been proven in the study conducted by Wall. So the crop evapotranspiration, it was estimated using the Powell-Penman-Montes equation that was adapted to remote sensing. So we were able to estimate the components of the crop evapotranspiration using the crop parameters that they were remote sensibly derived. For example, the net radiation, the heat flux into soil, the atmospheric conductance, and the surface conductance. So the effective rainfall was calculated using the semi-empirical model of interception, and finally the irrigation water requirements was estimated using the simplified approach by FAO. So for the results, this is just an example for the map of the irrigation water requirements, where we have the distribution of our values, the irrigation water requirements values. We have there our sector, our study area, and then the distribution of the values of irrigation water requirements. So when we computed those values, we were able to compare the estimated and the registered volumes. And as you can see that the estimated volumes, the variation of the estimated values is slight and simple, while the registered volumes are intense and sharp. And this is because when we were estimating our data, it was entirely based on meteorological data and on the satellite images, and we didn't take into account the operation of the distribution system. But when we gathered to a monthly irrigation volumes, we have kind of an agreement between the estimated and registered volumes with some slight differences. And for these differences, there are some hypotheses. Like for example, since we have 50% of the area is vineyard and it is wine grape, so maybe the farmers try to reduce irrigation in the growth stage of the wine grape in order to, because an excess of the irrigation can lead to affect the sugar content of the grapes. So we will have grapes that are good in quantity but low in quality. And sometimes it is because some farmers, they are using the wells and not our irrigation system. Like they combine between a well and also the irrigation system. So in order to compute the performance analysis, we have to determine the 10-day peak period, and we have the same notes as before. Well, the average estimated volume is 4,362 cubic meter, and the average registered volume is 4,643 cubic meter. And using these average volumes and the frequency distribution, we were able to compute the upstream discharge using the estimated volumes, which is the first graph, and the second using the average registered volumes. So we have 71 liters per second as a peak discharge and 78 liters per second as peak discharge in order to assess our performance analysis using COPAM. So COPAM, there are two models. The first one is the indexed characteristic curve, and the second one is ACLA model. So the indexed characteristic curve model gives us just like a global idea on the performance of our irrigation system. And here we have, well, the gravimetric elevation at the upstream end of the sector is 100 meters above sea level. So we have this point is 71,100. So our set point falls on the characteristic curve on 91%, which means that 91% of the 200 random configurations were fully satisfied. Using the registered volumes, which is 78 liters per second, we have the set point falls on the characteristic curve of 85%, which means that 85% of the configurations, they were fully satisfied. Now the ACLA model, it gives us the performance at each hydrant. So, and there are three indicators. We have the relative pressure deficit and the reliability indicator. So for the relative pressure deficit, we can see that we have some deficits in the hydrant 16, 18, 19, 21, 20, and 21, where we have like minus 0.3 as a deficit. And this is, of course, using the 100% envelope curve. And when we eliminate the 10% of the most critical points, like using the 90% curve, we have 3 hydrants where we have a problem. So using the second discharge, which is 78 liters per second, we have 8 hydrants out of 35 where we have a problem. This is using the 1% envelope curve, and using the 90% envelope curve, we have just 1. Reliability indicator, it gives us an idea on the reliability of each hydrant. So we have there a reliability of 0.7 to 0.8 for hydrant 16, 17, 18, and 19, and the same thing in the using the second discharge. And they are located there. So as a conclusion, what we see so far, the estimation of the irrigation water requirements volumes was accomplished through the estimation of crop evapotranspiration and the effective rainfall by combining crop parameters derived from Sentinel-2 images and the meteorological data derived from the atmospheric model ERA 5. So comparing the estimated irrigation water volumes and the corresponding registered volumes, the results showed a good agreement between the volumes in a large time scale for 10 days and 1 month period, while a large difference was observed in a daily time scale. So by transforming the estimated and registered volumes into discharges, the performance analysis was carried out at the global and hydrant level. The estimated discharge was lower than the registered one, and it reflected better performance. However, hydrant 16, 18, and 19 still corresponding to the most critical zones where we have the pressure deficits and where we should do some like for example, a boost pump, or if we want to invest, maybe increase the diameter of the pipe. Or just inform the farmers to irrigate in other period than the critical one. And if you want to know more about this, so this is the paper titled Analysis of Irrigation System Performance based on an integrated approach with Sentinel-2 satellite images. And that's it. Thank you so much.